Okay. Problem number two. We have, I can choose probably this color just to draw it. Okay. The problem is saying that we have a sort of piston cylinder arrangements like this. And it tells me that I have 100 gram saturated liquid. So I'll write saturated liquid, basically water, um, at T1 is 100. So at 100 centigrade. And it is now boiled. So now we sort of start heating. So let's say that heat is added here. You start actually heating the assembly, and until all the saturated vapor, sorry, until all the saturated liquid converted or becomes saturated vapor. In a reversible process, very important also in the reversible process because it also gives you a piece of information, and then it asks you find the work and find the heat transfer from the energy equation, and also we ask you to find the heat transfer from the entropy equation, because now we can find Q using the entropy. That is the input from chapter 7, which is using the entropy the analysis. It's going to make it, you're going to see it's going to make it a little bit easier. So let's draw before we, I will first define my system. So I take and I say this is my system, so the water inside is my system. And then of course we have some also assumption here, and the biggest one is that it's, or the most important one is that we have a closed system here, so the mass is constant, um, and okay, and then we can draw the PV diagram or TV diagram in this case, because we have T is the temperature is given. So it will, I can choose another color like this one, and then we, okay, the problem is saying is that, okay, doesn't matter. The problem is saying that I have um, water, saturated water, which is at this line. So this is point 1. And it tells me I start boiling. This is also very straightforward problem. I start boiling this until all the water becomes vapor. So this is a vapor. Um, and this happens if this is TV. So this is happening at 100 centigrade. And remember that the constant pressure lines are always like this. Um, and you can see that it's a constant pressure process. We could start at the start of the saturation, the start of the dome, and end at the saturated vapor line. And the problem is asking that we first using the energy equation, the one that we use in chapter 4, closed system, um, to calculate Q, which is the heat addition, and also it asks us to use entropy this time to calculate Q and compare between them to see if they are the same, basically. And we can start with, of course, what we know. I can write here, we know that the mass is 0.1 kilogram, and then it's a saturated liquid, so I know the state. So state 1 is saturated at T1 equal 100 centigrade. and then final state, you can say state 2. Again, everything is saturated vapor, still at T2 equal 100 centigrade. So you can see T2 and P2 actually is constant. So it's fully defined. Point number one, or state number one, state number two. So let's start with the first law of thermodynamics, because this is for closed system. This is your guide. The first law of thermodynamics, if it's an open system or it's a closed system, it's your guide because you will always use it. And then it's a matter of sort of writing down and then what kind of information that you need to gather to calculate or to determine the things that the problem is asking about. So if I say the first law of thermodynamics for closed system, Q minus work, I can write from 1 to 2, from 1 to 2 just to show that it's a process, is equal to the mass, it's a constant mass, so it's the mass multiplied by the change in internal energy. And we know this from chapter 4 already. And now it's just to, okay, let's see what we have. Let's see, when you write it this like this, do we know Q1 to 2? We actually don't know it yet. And what about the work? We don't know. We know that work is done here because we have expansion, but we don't have it yet. The mass is given, so we know it. You can write this is we don't know. We don't know. U1 and U2 we actually can read or can find because state 1 is fully defined and state 2 is fully defined. So the challenging now is that either you need to calculate the work so you can calculate Q, or you can calculate Q so you can calculate the work. So let's try to calculate the work. So what is the work? We know that for closed system or for boundary, it's an expansion work, it's a boundary work, and we know that the boundary work from 1 to 2 is actually PdV from 1 to 2. And that's, we know, since the pressure is constant here, it's V2 minus V1. And if you write, I will just draw it here, so things are, this is TV, and if this is 100 centigrade, so this is V1, and this is V2. Very straightforward. So I can see that V1 is actually Vf at T1 100. So I just go to the table at T1 100 centigrade and I read Vf there, because as you can see, that is Vf and that is Vg. And V2 is actually Vg gas at T1 100 centigrade. So I can also write here immediately because we're going to need it. U1 is the same. It's UF at T1 100 and U2 is UG at T1 100 centigrade, as you can see it here. This is state 1 and this is state 2. So if you substitute, or you can immediately see that this is actually pressure multiplied by VFG. And you know what this means? It means that Vg minus Vf. And if you write this down, of course you need to, please, the mass, don't forget the mass. I will sometimes forget the mass. You need to multiply by the mass to get the sort of the total work or the capital letter work. And if you put the mass here, multiply by kilopascal. Where did I get this number from? Of course, this number is, I can write it here, P. Both of them, it's a constant. It's actually the pressure at saturated pressure at 100 centigrade. You can also read it in the table at 100 centigrade, table A4. So I can write it also. All this comes from table A4, which is saturated temperature base tables. Multiply by Vg or Vg minus Vf. I can write it immediately here. 6718, and that is meter cube per kilogram. Don't forget this. And if you do so, that's going to give you 16.936 kilojoule. And that is the work. Now, if you have the work now, of course, it wouldn't be difficult to calculate Q, because Q1 to 2 now is actually M U2 minus U1 plus the work from 1 to 2, right? And the work we already calculated here, and this we have already, and this one we have, and this we have, so we can calculate Q. So Q1 to 2 equal to M UFG. I write it as UFG, it's because U2 is UG and U1 is UF. And you can also read it in some tables, you can read it immediately, this one. Plus work 1 to 2. And substitute the things that we know to calculate Q, then Q1 to 2 is equal to 0.1, which is the mass, multiplied by UFG plus the work which we calculated, and that's going to give you 205.7 kilojoule, and that is the heat transfer. Now you can also see how many ways that you can calculate Q. I can also say Q1 to 2 is actually the mass multiplied by the difference in enthalpy. So mass HFG. So that's also another way of calculating. You have also learned it before, and that's going to give you 1 multiplied by 225.703, and that's going to give you 5.7, exactly the same number like here. It's very interesting. It's very clear now. You see how we can calculate Q. So Q, either we calculate it by sort of calculating the work first and then add the work to the mass multiplied by the difference in internal energy. This is the second method that you can calculate Q, and that is Q equal to the mass multiplied by the difference in enthalpy. And you can see that it gives you the same number. And the third is using the entropy equation, as we can see it. And I can write it here. I can see entropy equation. And you know it. We said that M S2 minus S1, this is from chapter 7, is equal to the integration of dq divided by t plus the the S generation, or the entropy generation. Now remember that this is the general form. the general form of the entropy equation, which is the mass multiplied by the change. I can also write it. The mass multiplied by the change in entropy is equal to the integration of dq divided by the temperature plus the generation or the entropy that had been generated by doing this process. Now, very careful, be careful that if I have a reversible and a reverse process, and that's very important because in the problem it said that it was a reversible process. Um, and if you have reversible process, we said that the equality sign is prevail and there's no generation, so that will be 0. If you have reversible process, there's no generation, increase or decrease of the entropy, and that gives you this as 0, which means that um, I can write it down here. M multiplied by S2 minus S1 is actually the integration of dq divided by t, and this integration, as long as t is constant, as you see in this case, it's isothermal process, then this here will it will be very easy to quantify, because in this case it will be Q divided by temperature. And the temperature, we know it, this can be read from the table. So Q is actually the temperature multiplied by the mass multiplied by S2 minus S1. And this is temperature constant, it's 100, multiplied by the mass is given 100 gram, multiplied by, remember, this is Sg minus Sf at T is 100. You get this from the tables, and then I can write it down here that the final answer, I do it in different colors. So this is where we have the final answer, and the final answer, if you put the numbers, if you get this one and this one from the tables, this you have, and this is 100, you will find that Q1 to 2 equal to the I can write it, I need just to find the numbers, and that's 0.1 multiplied by 373.15 multiplied by 6.048. This is, you get it as SFG, read it from the table. Please notice that this has to be in Kelvin. Very important, the temperature here has to be in Kelvin, so you have to convert it to Kelvin. We had 200. We have 100 temperature plus 273, and that's going to give you 373.15. And if you do so, that's going to give you 225.68 kilojoule. And as you can see, it's actually this number and this number. It's not a big difference. Very small error in the two numbers. So you can actually use any one. Either you do this, so you calculate the work first, and then you add it up to the mass multiplied by the difference in turnover energy, or you can use this. This is the second way to calculate Q, is actually the mass multiplied by, I can write it here, dH, or you can use the entropy, and that's, as you can see here, this is the equation. So the three ways here are valid to you to calculate the change in the heat added. I'm sorry, to calculate the heat added or the heat needed. Thank you. Okay, we start with the homework assignment 6 using entropy. Um, that is problem number 1. Now, problem number 1 is saying that we have a turbine, so I can do this. So we have a turbine, so let's draw our turbine. And that turbine, of course, the function of a turbine is to give me power out, or to give me rotating, which we call mechanical work, and that can be converted into electrical work. And to do so, we have, of course, the steam is coming at the inlet, so I will call this 1, and exit at the outlet, and I will call it number 2. And when the steam comes in, it comes with high enthalpy, and then inside the turbine, we suck some of this enthalpy or this energy and convert it to work, and the rest, of course, goes with the working fluid out at the exit. Now it's a steam turbine, and it is quite easy problem in terms of that both inlet and outlet states are actually defined. So I can write here P1 is 1 megapascal, so that is given, and T1 is 200 centigrade. And we know now, I hope, that when you have two independent variables or properties, the state is fully defined, and it exits at 40, so T2 is 40 degrees, with the quality, which is X2 now, is 83. Again, it's also two independent properties here, the temperature and quality, and that will definitely defined fully the state. As you can see here, heat transfer, kinetic and potential energy is negligible, so we can neglect this. And then he asks us to calculate the power in in kilojoule per kilogram, and then it's also the change in the specific entropy from inlet to the exit. So it's quite straightforward problem. Now we know that for an open system, and we know for turbine now, I hope, because then I don't need to write the whole thing, but we know it for turbine, especially when we neglect heat transfer, kinetic and potential energy, we know that the work, so let's first choose the system. So this is my system, this is my control volume. It's good always to do it just to understand. So this is my control volume. And we can write first the work, the control volume, and if I do it in the rate manner, then it's actually the power, because the power is actually the rate that we are using the work or producing the work, divided by the mass flow rate, because as you can see here, I don't have any information about the mass flow rate. And he asked me here to find the power per kilogram of stream. So he's not very interested in calculating the mass flow rate here. And that is H1, enthalpy 1 minus H2. So as you can see, that it's quite easy, because the challenge now is to find H1 and to find H2, and we know that state 1 is fully defined and state 2 is fully defined, so it's very straightforward problem. Uh, but it's also good to, you need to remember, sometimes some of the problems will ask you about the assumptions that you have done here, but let's say that the major assumption is that it's a steady flow. The control volume is at steady flow. So the control volume is at steady state flow. That's very interesting because it means that it's just one mass flow rate. It means that M1 mass flow rate at 1 equal mass flow rate at 2 equal M. And that means that I don't have any accumulation of mass inside the control volume. Now we have another um, sort of assumption, and that is Q, potential energy, kinetic energy are negligible. So you can sort of, you don't need negligible. You don't need to take them into account. And by having these two assumptions, you can see that the first law of thermodynamics is becoming very easy. Form is actually um, the difference in the enthalpies. So the challenge now is to find those enthalpies. Um, and I'm not going, of course, to show you the table here. I've done it many times before, so I will sort of just explain how we can get, and I will write just the name of the table, uh, and you can check it out. So let's write again the work. The work of control volume divided by the mass flow rate, that is equal h1 minus h2, and then the challenge is to find h1, h2. Now remember, we said at, I can also write it here, state 1, just we have the pressure P1 is 1 megapascal, and then we have the temperature T1 is 200 centigrade, as you can see here. And that you can, if you know that it's a superheated, because if I usually when I send it into gas, into a steam turbine, usually it's superheated. If you don't know this, go to the temperature one at 200 centigrade, and then you will actually find that the temperature there is less than 200. So if the T1 is larger than the T saturated at pressure 1, then we know that it's superheated. So it's just to go to a superheated table. So I can write H1, I can read it as, so H1 is actually 2827.9, and that is taken from, I can write it here, superheated steam tables. It's A6 in your book at P1 equal 1 megapascal and T1 is 200 centigrade. If you do so, you can read H1 as 2827.9, and I can write it kilojoule per kilogram. Okay, that's H1. Now H2, as you can see, what do we know about state 2? I can write it also here. State 2, we know that T2 is 40 centigrade, and we know that X2 is 83. I can just check it out just to be sure. Yes, it's 83 or 0.83. Oh, that's nice. And then, of course, how can we find H2? Now, if you go to the table, you can see from here that is, since X is given here, and so it means actually that we are under the DOM. Um, I'm gonna draw it at the end just to actually you can decide. Sometimes I like actually to draw it at the start, but for this problem, because it's quite straightforward, I will draw it at the end, and you can see the two states. So H2 in this case, we know that it's saturated table, and since The temperature is given here. We know that we need to use saturated table temperature base, which is A4. Um, and if you do so, you'll find that H2 is, of course, HF plus X2 HFG. HF and HFG can be read at, I can write here, T2 is 40 centigrade and X2 is actually 0.83. If you have this, and those you can read from the table straightforward, and that's going to give you H2 as, I will write just the final results here, 65.1, and that is kilojoule per kilogram. So now I have H2. I can also write here the name of the table. It's saturated table temperature base, which is A4, just for the so you can track it. Okay, now we have H2 and we have H1. It's just to substitute it here to calculate the power. So if you substitute it, that's going to give you 2827.9 minus 2165.1, and remember this is kilojoule per kilogram, and that's going to give you 662.8 kilojoule per kilogram, and this is the power output of the turbine. Very straightforward. Okay, now he also asked to find a change in specific enthalpy. So what he's actually asking is, if we say B, find the change in specific entropy, sorry, which is ds, basically. Now again, it's also both states are fully defined. So from the same table, I also can write S1, and that's, I will just write it here first, and then it's kilojoule per kilogram Kelvin. Remember, that's the units for entropy. And where did we find this number? Of course, we found it. Remember, B1 is 1 megapascal, and T. Sorry, I need to do this. We take T1 is 200 centigrade, and we said that is superheated. We already used it to read H1, so you know where to go. And S2 is actually the same as we calculated H1, that is SF plus X2 SFG. Those can you read from table A4 at T equal 40 centigrade T2. And of course X2 is given as 83%. If you bring SF, SFG, and put them here, you will get 6.9506, and that is kilojoule per kilogram per Kelvin. So ds in this case is equal to S1 minus S2, and that's, if you put this number, of course, and this number, and subtract them, you will get that ds is 0.2366 kilojoule per kilogram. And I will write Kelvin here. And you can see it's actually very little. And that's because we also remember, we most of the time actually assume that there is no change in entropy in when steam is expanding in the turbine, assuming it's reversible and adiabatic. and this is why it's very, very small here. So it's quite straightforward, as I said, problem.